So thank you everyone for attending this talk. So a little bit about me, but then I want to jump quickly into the main topic. So my name is Guglielmo Iozzia, and I'm part of the manufacturing division IT of MSD, or Merck for people coming from the North America. And I mainly focus on leading some initiatives of applied computer vision, deep learning based computer vision in manufacturing. Lately also working on other machine learning, deep learning use cases. And that's my main field of expertise in this space. So you can see here some snapshot of some papers to which I gave my contribution on implementing and open sourcing the code. So let's jump to the core topic. Today I'm referring to a use case in machine vision, but really these considerations are applied to any kind of machine learning, deep learning initiatives. So because these are new paradigms that is a reality now, is not restricted to images or visual content, but any kind of data you would need to use for your machine learning purposes. Then I will share a successful use case of an application of this paradigm, just to show that these things really work, and some final consideration on the lesson learned, and a suggestion if you want to start the same journey in your organization for your specific use cases. So basically, if you are have some active machine learning, deep learning initiatives, you probably have noticed that there are the progress in algorithms in the last decade is impressive. In particular, if I narrow the scope to machine vision, but it's the same for other contexts such as NLP. We saw an interesting presentation from Bayer before on this. So these kind of algorithms are matching the human's capability in many tasks. There is an issue anyway, because which is related to data, because you need data to train and validate your models, and this presents some challenges that you're, I'm pretty sure, aware of, that often typically you have labeled data, but doesn't mean that this data is reliable. So there is still uncertainty, and the quality could be poor. So that there are different factors impacting on this that I'm not going to list here today. Also, what I'm observing with my collaboration with academia, and part of my job is to evaluate some existing papers to understand if, because we don't want to reinvent the wheel, some algorithms could be, or neural networks were better, it could be applied to our specific use case. And I see that in terms of algorithms, that's basically, there is plenty of choice for your use cases, but there is a very little effort in academia to think about ways to improve the quality of the data, or how to get good data. Narrowing the scope to computer vision, also some of these algorithms unfortunately don't generalize very well. So they have been trained on a specific domain. It's possible often to replicate the same experiment with the same results, but moving to a different domain, it doesn't work anymore. So this happens. So before you can select a specific algorithm for specific task in machine vision, you have to evaluate different options. And last but not least, probably you don't have the data you need, which it means that you don't have data at all, but in there are some cases where the data that you really need are not available. So you have some data, but probably not useful for your use case. So the new paradigm relates to the usage, generation, and usage of synthetic data to overcome some of these issues, in particular about data quality and data availability. And so it means that organizations are moving to working harder, to working smarter in terms of data, and of course machine learning, deep learning. And this is basically is happening in a different industries. Unfortunately, these things, these algorithms, these practices is used to generate some lots of deep fakes about the human faces. I'm narrowing here the scope to images, but really you can see deep fakes of different kind of data. Everything you see in this page is fake, and also those beaches. So the idea behind this new paradigm is that why not use this in a different domain? And so I'm seeing in the market several startups now available, providing services to generate synthetic data for you, in particular for images and or videos. So it means that if you don't have the capability in-house to train your generative models and start generating your synthetic data, you should rely on some external partners. Unfortunately, all these startups focus on some domains that are general knowledge domains, such as automotive, satellite imagery, or aerial imageries, retail. You understand that this domain is easy to understand for everyone, because everyone knows about what is information about traffics, cars, the environment where you can drive a car, or aerial view, or everything you can find in a scaffold in a supermarket. But when it comes to some domains where there is need of specific knowledge, such as, for example, pharma manufacturing, when I see it, but there are many others, would this be possible? Would this bring some value to the specific use cases? And this is where the idea in my organization started. So we try to overcome an issue we had by generating our synthetic data for a very challenging situation, so different from automotive or aerial images. So this the problem was part of work of a big program we have in-house, which moved to production for the first time in September 2020, to provide some advanced analytics and AI-based solution to the SMEs at the shop floor and the business, to get insight about the rejection and the quality of the inspection of our major products. As part of the solution, I could talk about it for days, so that's not the main scope of this topic, but I'm going to focus on a specific use case and problem. The solution provides some deep learning based models for visual inspection to do classification or object localization of images of rejected products based on certain defect types. Everything was fine since the first release to production from September 2020 up to spring 2021. But then we faced an issue because for a specific use case, for two major products of us in the immuno-oncology area, we didn't have enough images to train the model. Let's see what are the other challenges in this problem. You see in the right part of this slide a picture of a generic syringe. Please take a few moments to look at this, because this is the last time in this presentation you will see a syringe this way. So this really is how the visual inspector and machine learning engineers see a syringe, because these machines are equipped with 5 cameras. Each combination of cameras is used to address a different kind of inspection, different classes of defects. For this particular camera, which basically takes pictures of a syringe during the inspection at 30, 60 degrees, and then flatten them in a single bidimensional images. If I remove the labels on top of these images that I put here, it would be really hard to convince you that this is a picture of a syringe. So there are, I cut a little bit this image, because if you look at the full image, it would be more challenging. So where we are focusing for this problem is about these two areas here in the middle, at liquid level, where there is the products, because we are talking about pre-filled syringes with this vaccine, and the stopper area. So of course, there will be some pre-processing of these images that I'm going to show you in the next slide. The challenge was that for some of these defects, we didn't have enough image to think about training a model. Of course, we couldn't detach these classes, these categories from the problem, because they were really important from business standpoints to take decision about retuning machines or other major decisions. We tried different techniques, such as traditional data augmentation, or working with the SMEs at the shop floor to generate some tested inspection with test images that unfortunately weren't so realistic and good to train our models. The performance were really bad. And just to give you an idea of the situation here, these are the defect types that you as part of the solution. Those marked in red means that we have enough and good quality images to train the model. Those marked in red means that we didn't have enough. Also for liquid and ribs, it was a borderline situation because initially we weren't sure if we had enough images and avoid some issues of having some images out of distribution when moving at different time. These images here are coming from production expected batches after the preprocessing and after the labeling from the SMEs. You can see it's quite challenging because there is also a lot of noise. Just consider, for example, this situation here of a particle. This is a lucky situation where you can clearly see this particle, but there are others that are so small. And also we do now also some differentiation to understand which kind of particle is, if it's a fiber, if it's a piece of glass or something else, things like this. And also the background is constantly changes. There is a presence, probably don't know if you can see here on the bottom, there are bubbles because during the inspection, these syringes are shaken. And these are fooling the inspection machine. So that's why we're putting this model to double check and understand how many false positive we had for this. So you can understand the importance of this issue because it's not just financial impact, but also for the final users, because it means that if you have lots of false positive, false rejected, that you cannot bring into the supply chain downstream, means that there is a chance that some patients couldn't receive the treatment in time. So the idea was let's try to move to some generative approach and exploring different options. Before jumping into the generative models area, we tried to do some task analysis meta learning. It didn't work because it didn't generalize. So we tried two different implementation, two different families of generative models. The first one was the so-called variational autoencoder. The architecture of this neural network is quite simple. So there is input layers that receive images, and then they transform these images into a latent space, so a space with a dimension lower than the initial one. So basically, they do just noise reduction. Once you have this probability distribution into the latent space, then downstream you train the model to have a decoding layer that basically tries to reconstruct the initial input. So people not familiar with this architecture usually ask, what's the point of encoding something and then decoding it again? Let's go to see practically how this could work. In this picture, you see bidimensional representation of the latent space of the original inputted images. By the way, the variational autoencoder is a kind of approach that could be semi-supervised or unsupervised. Because in our case, we had labeled images and verified images. We use also the labels, but you could also do without labels for this. But in our case, speed up things. So basically, it means that we reduce the original input, removing all the noise from images, which could see as a multi-dimensional arrays, into a couple of points that you can represent in a XY diagram. So how to interpret this? This is something that I generate myself in from the original work. Unfortunately, I cannot share the interfaces of the app we have now, but this gives an idea on how this works. So you can see here there are different clusters of points of different colors identifying the different categories. And you can see here there are two distinct green clusters of points. And there is another one in yellow that is not of interest because it's related to accepted products, so not an issue at all. And then there is this area where you have overlapping of points of different colors. So it means that you cannot use this area here because there is overlapping between these images, their features. So you cannot reconstruct something realistic or useful for use case from here. So focusing on these two clusters. The variational autoencoder means that once you have these clusters, you send some input moving in a boundary of this cluster of this one to the decoder, and the decoding will produce images, realistic images, which belongs to the same category as this one. And so, just to show some example, moving, from, don't know if you can see this part of the screen. Let me move this here. So in this boundary, the decoder start to generate some images of incorrect stopper, which really are those to which this point belong. Moving to the other cluster, we start the model generating realistic images of inverted stopper, which were two of the categories for which we didn't have enough images. After these steps, we move these images to a next algorithm to do super resolution to align the resolution to the original images. So we partially solve the problem. We are not yet there. So what we did was to move to a different approach to a generative adversarial networks, which you can see here, a generic architecture on the slide. So basically, this architecture is made by two different neural networks, one called generator, which is trained by inputting real images, production images, by adding some random noise. And so it's trained to generate deep fakes of these images, while the discriminator is trained in parallel by inputting real images and fake images produced by the generator. That's why the term adversarial for this architecture, because this network were trained one each other. The equilibrium is reached when the generator is so good at generating fake images that discriminator doesn't have idea how to distinguish between real and fake images. So by training this model, which is more computationally expensive than the variational encoder, where here we reach this result in only 50 epochs, with GAN, we have to train the model for 5,000 epochs and in a more powerful multi-node cluster equipped with the GPUs, but while we didn't need GPUs at all for the variational autoencoder. As you can see here, there are a very realistic example of molding defects and dirty stopper defects. And of course, we couldn't use all the generated images for this use case. We have to discard around 30% of the generated images, not because they weren't realistic, but because they were too much realistic, presenting multiple defects at the same time for a single image, which is not the goal, was not the goal for our training. At inference time is fine if some production images comes with multiple defects at the same time for a single syringe, but for training, we want to train the model to detect specific defects. So what we did next was that we were wrong initially to think that this approach were mutually exclusive. At the end, we came up with combining these two architectures together. As I mentioned, the GAN is more computationally expensive. For other problems, we have to rely on different architectures. So this depends on the specific use case and images you're going to address. There are some metrics that you could use to assess the quality of these models, but the best way for us was to mix these fake images with real images and submit this for labeling to a pool of SMEs to understand if we could fool them. And definitely they came labeling these images and came with feedback saying definitely we are not able to understand which were fake or which are real. So we had clearance to use this to train our models. Then we start receiving new production images because production start again, and we train in parallel to two different models to get basically compare performance, and we realized that performance degradation by training with a mix of fake images and real images towards training with only real images was around 1%. So just to give you some numbers, the composite score by training with real images was around 93.3% in this use case, same for the F1 score, while for by training with a mix of images, fake and real, was around 92.1%. So really good performances that are still much confirmed by monitoring the model in production. And this was the test bed for us to open a new world for other use cases where we have the others where we definitely have to rely on generating synthetic images before training the models. Today I talk about images, but probably you have use cases in other fields. These generative models are a practical application in real life on a different situation. One of these has been described yesterday, the AlphaFold, by some talks from Alteryx, but there are many you can find in the real world. Before jumping to the QA question, I have try to answer one question that could come from you. So what if you want to start this journey for your specific use case? So definitely one thing that you have to keep in mind is what is the business value you're trying to realize for your initiative? If this is something that really is worth to move on generating synthetic images and train with that or not. So the business value it should be the entry point for this. Then when you're sure that you really have to do something this way, move fast, because the sooner you fail, the sooner you will succeed. And in terms of the algorithm, so the challenges are more on preparing the data, getting the data, have some labeled data, and collaborate with the domain knowledge stakeholders for this. The algorithms are your last problem. So you can use some existing paper, some open source tools that you can tweak depending of your needs. That's the same way we did for this use case. And if you can run this into a cloud infrastructure and use some data science machine learning platform, the better, because you will reduce technical depths. And most important of all, invest in people, both at each level, at domain experts, machine learning people, data scientists, software engineering, and have this one talk each other. So this is key. So if you don't have these talents in-house, then any tools or any infrastructure is totally useless. So this is the best advice I could give you in this space and in general for machine learning AI. That's all I have for today, and I hope you have time for Q&A, and feel free to reach out for any kind of questions or sharing your experience with generative models or computer vision in general. Thank you.
Thanks a lot, Guillermo, for this beautiful presentation. Insightful, really energetic. I love your positive energy as well. I just have the background Q&A waiting and hoping the participants will have questions, please. Let's see if somebody wishes to have a question that we can give microphone or read the question. Okay, it seems we have Angelo with a question. Wait a second. Angelo, I give you microphone. Let's see if you can read the question yourself. Angelo, unmute. Okay, go ahead, Angelo, with the question. Now you have
so my question is a bit technical, Guglielmo. So I wanted to ask if because GANs are difficult to train, sometimes unstable. So since you put this into production, so did you saw some problems there, or maybe mode collapse where images were all the same, let's say?
Yeah, so basically for this specific use case that I share, we face this issue by training with a small or medium number of epochs. So by running with a larger, as I mentioned, was 5,000 for to generate molding defects and dirty stopper images, was then stable on generating a variety of images and running more, also generating some images of liquid in ribs defects. For some other use cases, we had more challenging issues, and we have to move from a more traditional GAN to a conditional GAN. So basically it means that for the use case I shared, we use just the images without labels. In conditional GAN, basically you drive the GAN saying, please generate the images of this particular type. So it means that the GAN removes all the noise. And you say, if I want to generate, let's say, only liquid and ribs images, it's trained to do just that. And the GAN automatically start to exclude any details that are related to different kind of defects or categories. One interesting thing that we found for the specific images we had for this use case and the other cameras for the same problem is that GAN looks pretty good of generating images where you want to catch up small details into the overall picture, while they fail if you want to generate something bigger. So for example, if you would like to generate some human faces, that definitely is more challenging than doing something for these syringes. While the variational autoencoder looks like from the analysis from the team that is good at generating overall picture if some defects such as, let's say, inverted stopper or bubbles are filling the full image. So we have other use cases that where did face this, but moving to some conditional GAN algorithm, we solve the problem about stability.
Thanks a lot. Thank you so much.